Let's talk about Taylor and Maclaurin series. So earlier, we looked at how to represent functions as power series centered at A. Now, in the past, what we did was we had used tricks and substitution and derivatives and integrals in order to basically manipulate like geometric series to get functions as power series. But in this section, we want to find a nice formula for the coefficients. These coefficients right here, these different Cn. And we're going to find a pattern by using differentiation and substitution. So this is a more mechanical way of finding a power series representation for a function. So let me show you what I mean. If we look at this power series for f of x, and let's say I just want to find the C0 coefficient. There's an easy way I can find C0. Okay? So how can I find C0? Well, notice that if I substitute an a in for x, then all these x minus a's are going to equal to 0. So by virtue of the fact that just substituting f of a, substituting a into f, we're going to get C0. Okay, so what about C1? How am I going to calculate what C1 is going to be? Well, what we can do is we can first take the derivative f prime of x, and let's see what we get. When we take the derivative of prime, the C0 term disappears. The derivative of the second term, C1 times x minus a, that's just going to be C1. And then when we look at the rest of it, we're going to have plus 2 times C2 times x minus a plus 3 times C3 times x minus a squared plus blah, blah, blah. The general term is going to be n times Cn x minus a to the n minus 1. What I want you to notice is that every term except for the C1 term, all these other terms have an x minus a inside. So if I did the same trick, if I simply substituted an a into f prime, so I substitute an a in for x, what am I going to get? I'm going to get C1 surviving, and basically all the other terms are going to be equal to 0. So this gives me a nice formula for C1, and C1 is really just going to be f prime of a. Great. Let's try to find C2. Leave just a little bit of room under your notes where the C1 is, just a little bit of room because I need to fix something in a second. So let's take a look at C2 now. C2 is going to be equal to what? That's what we're trying to find, right? So I'm going to do the same trick that I did before. I'm going to take a derivative. So I'm going to take the second derivative, which is the derivative of the first derivative. And what's going to happen there? Well, what's going to happen here is the derivative of the C1 is going to be 0. And when I take the derivative of the second term, what I'm going to end up with is I'm going to end up with 2C2. And the x minus a part is going to go to 0 when I take the derivative. So I end up with 2C2 plus, now let me take the derivative of the second term, that's going to be 3 times 2 C3 times x minus a. And then the next term is going to be, or rather the general term is going to be n times n minus 1 Cn x minus a to the n minus 2. Okay, so again, we can see if I manage to substitute in an a in for x, every term except for the first term of the second derivative is going to go to 0. So if I do f double prime of a, that's going to give me 2c2. And that if I solve for c2, that's going to give me c2 is equal to f double prime of a divided by 2. I think calculating one more coefficient will make the pattern clear. Okay, so let's try to find C3 now. So C3 is what? Well, I'm going to take the third derivative of f. So when I take the third derivative of f, what do I get? This first constant term is going to disappear. What remains for when I take the derivative of the second term is just going to be, and watch how I write this, this is going to look a little bit weird, but it's going to be 3 times 2 times 1 C3. In other words, I think of this as x minus a to the first power. I bring the 1 down in front. I subtract 1 from the power. That means x minus a to the 0 power. That's equal to 1. So you got 3 times 2 times 1 C3. And then when we keep differentiating the rest of the terms, we're going to get that the general term should be n times n minus 1 times n minus 2 times x minus a to the n minus 3, and so on. So what happens when I substitute in a for x? When I substitute in an a for x, I am going to get f triple prime of a is equal to, let me write this as 3 factorial times c3. Okay, then this tells me that my c3 is equal to f triple prime evaluated at a divided by 3 factorial. Great. So I'm going to highlight this. This is our coefficient C3. I want to revisit the coefficient C2. I want you to notice that 2 is the same thing as 2 factorial. So I could really rewrite this as C2 is equal to the second derivative evaluated at a divided by 2 factorial. And let me highlight that coefficient. And I can really rewrite C1 as, instead of just putting an f prime over a, I can really write this as f prime of a over 1 factorial. And if I highlight that, that's going to be the C1 coefficient. Okay. And let me go back and let me change my C0. My C0 is really the same as f of a divided by 0 factorial. And this is true because this is since 0 factorial is really equal to 1 by definition. So that means that my C0 coefficient is just f, really the 0th derivative of f evaluated at a over 0 factorial. So look at these coefficients. You can see that when you look at the index is going to correspond to which derivative we take. And it's also going to correspond to the number that we take the factorial of in the denominators, right? So if I were to ask you, what do you think the fourth derivative or the fourth coefficient C4 is going to be? Well, I would guess that you would have to take the fourth derivative, you evaluate that at a, and then you divide by 4 factorial, okay? So if we continue on in this pattern, what we've just done is we've found a pattern for what the CNs should be. So from this, we see that our Cn should be equal to the nth derivative of f evaluated at a divided by n factorial. So this is a very mechanical way, assuming we could find derivatives and factorials easily, that we could find the coefficient. All right? Okay. So now we are in a position to define Taylor and Maclaurin series. Okay. So if F has a power series representation, we sometimes use the word power series expansion, at A. In other words, if we could write f of x as a power series with a radius of convergence r centered at A, then its coefficients are going to be given by really what I just wrote earlier, Cn equal to the nth derivative of f evaluated at A over n factorial. Highlighting that again. And this object is called the Taylor series of f at A. We sometimes say about A or centered at A. This is different ways of describing the center being A. Okay. We have a special case called the Maclaurin series. And the Maclaurin series is the special case where this A is actually just equal to 0. So if I wanted to write the Maclaurin series, f of x is really just going to be equal to the sum as n goes from 0 to infinity. We're going to get the nth derivative evaluated at 0 because our a is 0 over n factorial times x to the nth power. So I'm going to highlight this Maclaurin series. This is a special case of a Taylor series. Okay. So we will be looking at examples in class together where we're going to take a zillion derivatives and try to see if we can't write a nice pattern, see if we can find a pattern for the coefficients, and then we can describe our power series in a very neat way. All right, everyone, take care.